Okay, here we are once again. Welcome to the Physics 2A video lecture. And what do we have here? This is Physics 2A video lecture 7. So this is the last one for this week before spring break. And I'll start with some announcements. So the homework and the notes are due Friday, April 3rd. And after spring break, we'll have probably 2 review lectures, and then we'll have exams on the 16th and the 17th of April. And they are scheduled for the normal time that was on the syllabus, so the normal class time. And I'll give you the details of how we're going to do this when we get back from spring break. But roughly speaking, it's going to be the way we've been doing the homework. By that time, the pictures are going to have to be very clear because I'm not going to print them out. I'm going to read them on my screen and grade them and send you your grades. It's going to work, okay? Just for now, though, all we have to do is keep taking good notes and doing our homework. And today, I didn't bring any demonstrations. I thought we had a nice run of demonstrations. I'm going to mostly solve problems, review what we did, take a look at that homework problem with the bag there in the hospital, and then do some buoyancy problems. After that, possibly we'll get into fluids in motion. But right now, we really want to work on the buoyancy problems. It took some time to get there, and I've built it up, so now we want to do some of these problems. And the formulas that we have, so this is fluid statics, but I'm just going to write fluids. We had the density. That was the Greek letter rho equals mass per volume. We talked about the units. And equivalently, we also want to know that the mass is the density times the volume, okay? Because we make use of this in various problems. That's the density formula we're going to use. We had the definition of pressure, where P, the pressure, is equal to the force divided by the area. And we can also, and often do, use that the force is equal to pressure times area, right? These are equivalent, come right out of the definition. Okay, so those are basically definitions. Then we have the pressure depth. So I'll write pressure depth formula. I'm basically writing down the formula sheet for this section. Okay, so the pressure depth formula, P is equal to P0 plus density GH, where H is the depth. And I'll put here that the atmospheric pressure, which is often P0, is often the atmospheric pressure. Here I'm going to abbreviate it, P atmosphere, is 1.01 times 10 to the 5 Pascal, which is newtons per square meter. And you can tell, we're just going to use the 1 on our exam, right? We'll just use 1 times 10 to the 5, a perfect number to use. Just like we use G is equal to 10. Yeah, and then we have the buoyancy formula. For buoyancy, the buoyancy force, and that is F sub B is equal to density V G. Okay. In words, it's the weight of the displaced fluid, because this density is not your object that's being acted on, it's the surrounding fluid. So density of the fluid, the volume that's been displaced, and G. Okay, so those are our formulas, and we're going to become accustomed to using them, and I'm going to give you several nice examples. The first example is from the homework, though. So homework example, I think this was problem 11. there were a couple of concepts I hadn't mentioned. There was the gauge pressure, so I'll put that right now, the gauge pressure. Actually, that's UA. Is equal to P minus P0. So it's actually just the left side of this equation. You take P minus P0 and you've got that rho GH. So that was the gauge pressure, and it's typically, or it's very often far less than the atmospheric pressure itself. Okay, after all, the atmospheric pressure was that crushing pressure. So, hold on a moment. Okay. So what did we have? I can't draw an arm, but who can? So there's an arm, and there's a hand on the end of it, and here's where the drip was going in, and there's that bag. Okay. And you'll notice that the H was from the top of the water line, or whatever the solution was, down to the point of entry. Okay, that's because the H is just the entire H, regardless of height difference, regardless of shape. Okay, it's just all of this here. This was a hollow tube, all the way down to there. So yeah, we had that T minus P0 is equal to rho GH. Now this P minus P0 was given, so we had H was equal to the given P minus P0 over rho times G. Now the density here was the fluid in here, okay? And then G of 9.8. This was that number that was given, and the result, it was in the book, it was 0.133 meters. 0.133 meters. So, that's interesting. In order for this thing to actually, and if you've been in the hospital or been with somebody in the hospital, right, they have a bunch of these hanging from a rack. Somebody's all intubed, okay, they're coming in there. They have to be hung high enough to overcome the internal pressure, okay? And, the higher you hang it, the more excess pressure you'd have, it would drive it in faster. But if you were to hang it too low, you won't overcome the pressure and nothing will go into the body. Okay, so that's an interesting problem. Interesting problem, and you can see it was just a direct application here of this formula. Okay, so now I'm going to move on to the problem that I ended with last time. I think that one's worth doing. There's our eraser here. That one is worth doing. I'm probably going to have to erase most of these formulas here just to have some room. Or we can just do one at a time and get rid of the atmospheric pressure here. And these, okay, we'll just stick with the original definitions. That should give us enough room. Okay, good. Okay. What I left us off with, and what I'm going to start with, is this classic problem of finding the volume of an object that's suspended in a fluid. Okay. In the Archimedes story, it's a crown that's been, where a little gold has been embezzled. Okay. And in our story, it was an engagement ring or something. I want to know if it's platinum or tinfoil. Either way, in a problem like this, we're just setting up Newton's law with the new force. Okay, so we have the weight of the object. There is a tension in the string. And so the weight of the object is the weight of this object when you weigh it in air. And so that's its actual mass. And here the tension is what you weigh when it's slightly supported by the buoyancy force, which is also acting on it. So F sub B. Okay. So from here on out, I could even say F net equals 0 to get the ball rolling on this problem. F net is equal to 0. It's a static problem. We have T plus the buoyancy force rho VG minus mg is equal to 0. And we did this last time. I'm just repeating it because it's an important problem. We're solving for V. And V is equal to mg, which is the weight when you just weight it in the air, minus the tension, which is the weight that you're reading when it's in the fluid. And then since we brought that over there, we just have to divide by rho and g. And this rho is the rho of the fluid we're immersed in, typically water, but not necessarily. Yeah, and so that's the volume of the object. Try to get the volume of a ring or something. You're going to have trouble. But if you have a delicate scale and a delicate thread and you do this experiment here, you're going to nail it. Okay? You're going to get it very accurately. So all of these things have been measured. You've weighted in air, you weighted in the water, you divided by, oh, got a mistake here. That was G. Love it when I catch my mistakes. Okay, rho times G. You can make that correction too now, right? Rho times G, we solved for B. So that's the volume. Then density, if we need to know it, of our object is its mass divided by the volume that we just found. So this measurement gave us the volume after a little calculation, the mass we had gotten before. Now we have the density. Okay, so that really is the prototypical buoyancy problem. You can do this one, you can do the rest of them. Okay. And you see, we like to be systematic. We've got Newton. We just write this down to get oriented, and then we say we have these steps. Okay, for the next problem, I'm going to take it another step. I think this will work. We'll keep these formulas on the board. We'll just use this board here, do them one at a time. Nothing wrong with that. Okay, the next problem is of some interest. So what we're going to imagine is that we have water. So this is the ocean, and there's an iceberg here. And you've probably heard that if there's some ice above the water, there's quite a bit more beneath the water. And if you don't believe it for ice cubes, for icebergs, just drop an ice cube in a drinking glass and observe carefully. Most of the ice cube is underneath, there's a little bit above. Okay. So this is a perfect buoyancy problem as well. So what are the forces acting on this iceberg? Here, let me label this iceberg just so we... Okay, so what are the forces? Its weight and the buoyancy force, rho VG. Okay, now this one's going to be interesting too. Very simple problem, right? Iceberg floating in the water. It could have a bunch of it underwater. By the way, if you ever look up some interesting iceberg type of videos, you'll see some neat stuff. So this one could have been here, and then a ship comes up to it and thinks they're going to get that far, and they collide. Okay, the Titanic. Yeah, since I'm on the subject, if you look up some of these iceberg videos, there's some interesting phenomena. Because sometimes, they're very odd shapes, and what people have recorded is they're on a cruise ship up there in Alaska or somewhere. Suddenly a giant iceberg will spontaneously just seek another balance, and it'll actually turn over. And it's giant, slow motion, rolling over and assuming a different position. Okay, so not boring at all. Yeah, so let's go ahead and do this now. So there's Newton, or here's Newton, F net equals 0. And we've got the iceberg buoyant, so we have rho Vg minus mg is equal to 0. So far, so good. Now here's where we're going to make a substitution. This is going to be the density of water times the volume submerged. Remember, the volume of the weight of displaced water, so the V submerged is just this part here. Okay. It's the part that's underwater, and that's going to be equal to, I'm bringing this to the other side, mg, but m is the density of ice times the total volume, total times g equals 0. Okay. So here's an important step. Remember, I told you that doing m equals rho times v is a common move, and here we see it. So now we have two different densities. Oh, by the way, there was a g here. Sorry about that. Vg. So we have density of water, v submerged, times g equals density of ice, v total. Total volume of the ice. Density times volume is mass. Okay, the g cancels. And here's what I'm going to solve for. V submerged, I'll call it V sub divided by V total. Yeah, what is that? Have a look. V submerged divided by V total is equal to density of ice divided by the density of water. Yeah, so that's about 9/10. I gave you those densities the other day up here. You look them up in the book. It's just about 9/10, 0.9/1. So 9/10. So 9/10 of it is submerged. The submerged volume is 9/10 of the total volume. Okay, so we get that out of there. Didn't have to plug any numbers in. So that's our iceberg example. Now, I have on the homework a problem that's like this, except you have the iceberg and then you drop an added weight on top. What's an added weight on top of this iceberg going to do? Suppose there's an Eskimo standing on top. What's going to happen? It's going to make it sink. It's going to go in deeper. And depending on the added mass, that's going to determine what happens. Okay, so the homework problem is a floating cube of wood, and then they're going to have a mass on top and ask you how much it presses it in the water. But just remember, you're always just doing your Newton's law, and if you had an added mass on top of this, well, then that would be an added weight in the down direction. Okay, and an added arrow pointing down. Okay. So now we have that classic one that I did twice, the Archimedes problem. We have the iceberg. The next one that follows the iceberg is the balloon. So the helium balloon is interesting too. Everybody's seen a helium balloon, probably held one in your hand with a little string on the bottom maybe. So let's call this the helium balloon. But now this balloon is floating in the air around us. In fact, if we let go of the string, it's going to float up and away. So let's take a helium balloon, and there's the balloon, and you've got your string right there. It's a helium balloon, and let's just do Newton's law with this thing. This may be surprising to you because you got to ask yourself, why does that helium balloon want to escape? Okay. So, helium balloon, helium in here, that's a gas. And what are the forces acting on this balloon? We have I'm going to write M of the balloon times G. And actually by this M of the balloon times G, I'll just call it M sub B times G. Here I'm meaning the balloon, the string, what have you, whatever you've got attached to the holding, that's the load. Okay, the total load includes the balloon. Okay, so get that out of the way. Then the helium weighs something. You know, it's a gas lighter than air, you know that, but it weighs something, so we're just going to say M of the helium times G, and then the third force is the buoyancy force, F sub buoyancy. And if we say F net equals 0, then that would tell us, we could use that to know how much of a load can we put on this thing. If we said F net equals MA, then possibly that would tell us when we let go of the string, it floats away, okay? So I'm going to just do F net equals 0 and say that's the amount, including the load, the balloon here, the load that would keep it just hovering, okay? So if you had a helium balloon with a string, you don't want it to float away, you put a little weight on it, and just it'll stay here on the table. You make the weight small enough, it'll just hover. That's our plan. So here we go. FB minus mass of helium times G minus mass of all the other stuff times G equals 0. So the buoyancy force, density of the fluid, volume displaced, and it's the entire spherical ball there, times G. What fluid are we talking about? It's not water, is it? The density of the fluid we're talking about is the density of air. So, do we know what the density of air is? I'd have to look it up. I think it's approximately 1.3 kilograms per cubic meter. Kind of surprising. Of course, it's 1/1000th almost, or 1/800 of the density of water, but still, you got a cubic meter of air. A kilogram is a chunk of, a fist-sized chunk of iron. So, good. 1.3 kilograms per cubic meter. Then we have the mass of the helium times G. That helium has a mass, okay? And we're again going to use this density times volume times G. So now I've done that substitution for a second time. Mass is equal density times volume, okay? So we're talking about the density of helium, same volume times G, minus the mass of everything else times G is equal to 0. And this time we see the G's are going to cancel. I'll strike them in red. And we can basically solve for one unknown. So in one sense, I could just leave this up here, because we could solve for one unknown in this thing. For example, given a volume, then we could say, well, how much can this balloon lift? What would its payload be? So then we would solve for M sub B. Given a payload, we could say, well, how big does the balloon have to be in order to lift that payload? So maybe I'll put that down as a note. Solve for M. I'll call it payload. Of course, the payload includes the mass of the balloon itself. Okay. Payload, if given V, solve for V if given M sub payload. Okay. M sub load there. Okay, yeah, so we set this up. You can see now we've already used this mass equals density volume version twice, and we have to be really careful about whose density we're talking about. The balloon is actually floating in air just like a block of wood floats in water. Okay? So if you release a block of wood from underwater, it's going to rise unless you hold it with a string. If you release a helium balloon in air, it's going to rise unless you hold on to the string. That's the idea. So good, we've got our helium balloon. And you know, I think these three examples are the ones you have to know in order to get through this part of the chapter. These are the three problems. They're very typical. I'm going to go ahead and write up what homework I had for you before I forget. And then we can see how much more we want to do here. This is definitely test material because we're well within the chapter here. So yeah, my new homework problem idea was homework chapter 9 problems. What did we have here? Problems 22, 26, and 27. And they're very close to what I've done. These three examples. A little modification, maybe pretty direct in some cases. Good. Okay, let me check something here. Okay, we have a good opportunity to move on. So those problems, and now we're going to go from fluid statics to fluids in motion. Spend a little time on that. So next, fluids in motion. Now, the phenomenology of fluids in motion is so rich that we can only cover a very small corner of it. If you want to see how rich it is, just look at the weather map. Okay, nowadays the weather report is accompanied by maps and really dynamic pictures of fluid flows, of vast air masses, across the continent, across the local areas. And there's all kinds of swirling and wavy motion going on. If you've ever seen a picture of Jupiter, Jupiter has all kinds of lines and fluid swirls, and the red spot, gigantic hurricanes on Jupiter that are bigger than our Earth. Those are all fluid problems at a really dramatic scale. Of course, we have to start out a little more basic than that, don't we? So our fluids in motion, we still get to cover some interesting phenomena. Okay. So when we're talking about fluids in motion, we have to first of all derive a couple of important equations. And the first one, I'll just name it and then I'll show you what's going on. Actually, how about I just draw a picture of a pipe with a constriction. Okay. Pipe with a constriction. In fact, there's a nice homework problem where there's a syringe, and that would be something with a very tiny constriction. But if you have a hose with a nozzle on the end, you know that the water comes in here and it squirts out much faster. Okay, it squirts out much faster. So why is that, or what is that an example of? Expression of. Okay. And in fact, suppose we had the pipe with a constriction and we made it wide again, and it was the same amount of water flowing through each side. You could say, well, it must be going slower here, faster here, and it slows down here again. Okay. So that's an application, what's called the continuity equation. So with the nozzle, maybe I'll draw some lines in here. You have slower, faster, slower. Okay. speed of the fluid. Okay, write that. Speed of the fluid over here, slow, and then over here, fast. Okay, so let's get a little more quantitative with that. So this time we'll draw the same constriction, and we'll say it has a cross-sectional area A, so cross-sectional area A sub 1, and it has a speed V sub 1. And then over here it has a cross-sectional area A sub 2 and a speed V sub 2. Speed or velocity V sub 2. Now, area times velocity has the units meters squared, meters per second. So actually, let's go ahead and do this. Let's write down density times area times speed, and look at its units. That's kilograms per meter cubed, and then here we have times meters squared, and then here we have meters per second. So what's left over? Meters cubed cancel against these, so the units are kilograms per second. So what this thing is called a flow rate. A flow rate, and if the mass is conserved, then the flow rate has to be the same in the wide part and the small part. Okay. So the flow rate is the same. Let's go ahead and call this whole thing is the flow rate. So the flow rate, which has been defined here, is constant through the constriction because the mass is conserved. You know, the kilograms per second have to be the same because it's not going anywhere. Okay. It's just flowing through the pipe. So flow rate is constant because mass is conserved. In other words, the mass is constant, the mass isn't being created somewhere, so mass is conserved. Okay, I'm going to use this part of the board to draw my conclusion. This goes under what I'm talking about here. If the density is constant, if the density remains constant, in other words, if this letter rho is constant here, then we end up with A1V1 is equal to A2V2. It means that I can write rho 1 A1V1 equals rho 2 A2V2 as an equation. I can cancel the density from both sides, and this is called the continuity equation. The continuity equation. And it even says, yeah, if the cross-sectional area is larger, V is smaller. If the cross-sectional area is smaller, then V is faster, V is larger. That's exactly what we experience with the nozzle, okay? So this is called the continuity equation. Very basic, but it's the basis for everything that would follow. Continuity equation, that's singular. Continuity equation. So look that up, you'll see it's in the book as well. Now this density constant is itself interesting because a fluid can be water, but it can also be air. And if you have an airflow that's fast enough, the density is no longer constant. On the other hand, if the airflow is not too large, in fact the case where it's really large is the speed of sound, and that's a long ways away. So air will Um, Air will satisfy this equation, no problem. On the other hand, if you've ever pumped up a bicycle tire with a bicycle pump, then you know that air can of course be compressed considerably. You can feel it being compressed, and then you know the density is changing. In the case of pumping up a bike tire, the density is changing. Good, so we've got this continuity equation. And what is a good example for it? Well, the nozzle, of course, is a good example. Here's an example from day-to-day life for the continuity equation. You've often seen water running out of a faucet. Okay, and if it doesn't have an aerator on it, it just can come down as a stream. And if it's just kind of trickling, you see the water taper off until it gets so small that it'll break up into drops. Okay, so that's water coming out of the faucet. And good, the cross-sectional area A1, call that A1, is greater than A2. Where's the water going faster? It's picking up speed as it falls because it's just in free fall. And so you could actually, if you were ambitious, it's not that hard, find out the mathematical shape of this taper just by using the continuity equation and the law of free fall. Okay, so you'd have A1, you'd have V1, A2, V2 down here, and the speed is greater, here it's lesser. So there's an example of the continuity equation that goes beyond the nozzle. There are others as well. I'm going to consult the text to see if there isn't a good continuity equation problem for us. Okay, in order to do these interesting problems, I would have to do Bernoullis equation. See if we have time to get there. Yeah, let's do one more example. Okay, good. We've got the continuity equation. If we had a formula sheet going, and you probably do, then we would add this one to the list. Okay, you've got that there. Let's okay, first I have to say a couple things about fluids in motion. So fluid flows laminar versus turbulent. Laminar, you could say, is a smooth fluid flow, and turbulent flow is a chaotic fluid flow. Actually, a nice example of this, there are so many, but if you have a candle burning and you ever snuffed a candle, okay, so I'll have a candle here. There's its flame. If we snuff the candle, then we'll see a little train of smoke going up. Actually, if someone's got a cigarette on the edge of an ashtray and it's just got some lazy smoke curling up, you snuff the candle though, and we haven't gotten to thermal physics yet, but the reason the smoke is rising is because there's actually a fluid flow of air that's been created. So the part where you get this smooth flow, that's still laminar, but you get up high enough and it just gets complicated and dissipates, and that's the turbulent flow. Okay, you have the laminar versus the turbulent. You can look up that for some more definitions. What we've been talking about is best dealt with laminar flows. Now the stuff going through the nozzle can certainly be turbulent, okay, no problem there. But what we're going to do next when we want to talk about fluids and conservation of energy and things, then we need to have a laminar flow, okay? So I'm going to add something to these definitions. Ideal flow, ideal fluid flow is, first of all, incompressible, we already talked about that, and then it's laminar, and we just talked about that, and finally it is frictionless. And you know, those are some conditions that can't always be met, but they are met often enough that you know, we get some useful information out of it. We did frictionless motion with free fall and projectiles, and we learned a lot. Okay. So similarly, in fluids, there are cases where these things hold, and then you can apply what I'm about to show you. So what I'm going to do next is Bernoullis equation. And sometimes I enjoy deriving the whole thing and making use of these categories here, but this time, under these circumstances, I'm just going to write it down, and we'll get some decent wisdom just from writing it down. So here's the idea. We have a y-axis, and gravity's pointing down the way it does, okay, so positive direction in the y-axis. And we're going to consider a laminar flow. You can imagine through a tube or something. But it doesn't have to be through a tube. So we're getting a laminar flow here. Okay. And we take a point and call it 1. I could do A and B as well. Have another point and call it 2. So Bernoullis equation is actually derived from energy conservation, and I write it down, you're going to see it looks like energy conservation. Here it is. It is that P sub 1, the pressure at point 1 plus 1/2 density V sub 1 squared plus density Gy sub 1 is equal to a constant, or we can say it's equal to P sub 2 plus 1/2 rho V sub 2 squared plus rho Gy sub 2. So yeah, just looking at it this way, it looks like it comes from energy conservation, doesn't it? Because that looks like kinetic plus potential, and in fact, the pressure terms, if you take P1 minus P2, if you put them together and multiply them by a volume, they're the work. So this is actually a work change of energy theorem, okay, which we've seen before in mechanics before. So that's what this is, Bernoullis equation. That's why we need frictionless. So it's a work change of energy. How about I put it in a red border? Put some color into this operation here, okay? So that's Bernoullis equation, very famous, very important. The Bernoullis are a family of geniuses. Forgot which one even did this. They're all over the place. Okay, so what we'll do is an application of this, and then I'll be able to assign one problem for this, and we'll call it good. Okay. So let's erase this. We got to keep Bernoullis equation up on the board. And the application that I'm going to do, example, first of all, we're just going to let y sub 1 equal y sub 2. So that's a horizontal flow. And in fact, what we're going to do is look at our constriction. We'll take a constriction. Okay, we know from the continuity equation, we've got V1, V2, and over here it's V1 again because it opened up. And let's go ahead and write down Bernoullis equation. The two y terms cancel because it's horizontal, or not cancel, they're equal on both sides, so we can drop them. So we have p sub 1 plus 1/2 rho p sub 1 squared equals p sub 2 plus 1/2 rho p sub 2 squared. So what is that going to tell us? This is a very surprising thing. We tend to think that, okay, if the speed is faster of the fluid, speed is faster, then the pressure must be higher, but it's exactly the opposite. See, this is equal, the left side is equal to the right side. If the pressure's bigger, the speed must be slower. If the pressure's lower, the speed must be higher. So in fact, there's a higher pressure, there's a lower pressure in this constriction than there is on either side of the constriction. It's truly a counterintuitive result. You know, if I had 2 sheets of paper, I could do a demonstration. Let's see here. See if I can find some paper. There's paper when you need it. Okay, didn't have to go far. This is a demonstration you guys can do at home. It's very, very simple. Got 2 sheets of paper. I don't know about the contrast in this room, but okay, I've got 2 sheets of paper. I'm just going to blow between them. I'm just going to blow between them, and they're pulled together, okay? So I just blow between them, and they come towards each other. Them coming towards each other means the pressure outside is greater than the pressure inside. They're being pressed in, okay? By a little bit of pressure difference, not the full atmospheric pressure, but once again, so you guys can do this, you just suspend some pages like this, blow right between them, and they're drawn towards each other. So that's the proof of Bernoullis equation. So let's put here in words, V is smaller when P is greater, and vice versa. Counterintuitive, but true. Okay, you know, there's a lot of other things we could do with this, but I'm going to call it right now and just put an interesting homework problem that goes with this topic, and that is chapter 9, problem 37. 937. See if I can set that up for us. Yeah, it's actually, this is a really nice one. Go ahead and erase this. The idea on this problem is that we have a hypodermic syringe, okay? So there's this part, there's a plunger here, and then it's going to, of course, taper down to a very thin needle. And we're going to shoot out some fluid into the air. So, okay, it tapers down. Let's see what else we have here. Okay, then there's a plunger here with which we're going to press on this thing. We're going to apply some force to this thing. Plunger sticks out like that, so we can put our thumb on it, press it in. Picture's better in the book. And yeah, then we will have some fluid in here that can shoot out. Now, the interesting thing about the fluid that shoots out okay, press pressure, and then the one syringe is horizontal. So you'll have to decide if you're, there's a force pressing on this side, okay, F, and it's labeled. You'll have to decide if you're using continuity, Bernoulli, or both, okay? I'll just note that we have atmospheric pressure out here, but they're asking us for the speed in here, okay? And what do we have out here? We have atmospheric pressure, but we're also pressing on this thing with an added force, okay? That's as far as we're going to get in this in the problems for the fluids in motion. Conceivably next week or the week after spring break we could talk about it a little bit more, but as you know, we want to then get to our review, so we'll have taken it up to here. Not a bad place. Okay, everybody, take good notes and have a good time in spring break, and we'll see you next time. Okay, this is it.